Hey everyone, and welcome. Today, we're going to talk about something that's literally all around us, but most of the time we can't even see it. Texture. We're diving into a technology that uses microscopic patterns to completely change the properties of everyday materials. It's called microembossing, and trust me, it's quietly reshaping our world. So let's just kick things off with a big question. What if we could solve some of our toughest problems, like making solar panels way more efficient, or creating security tags that are impossible to forge, or even building surfaces that can heal themselves? Not by inventing some brand new exotic material, but just by stamping a tiny, invisible pattern onto the stuff we already have.
Okay, so let's get into it. What exactly is microembossing? How does this whole thing actually work?
Honestly, at its core, the idea is incredibly simple. Seriously, if you've ever used a waffle iron, you pretty much get the basic principle. You've got a mold, the iron, and you press it into something soft, like batter, to give it a whole new shape and texture. Microembossing is just that, but on a scale so small you'd need a microscope to see it. So here's the official textbook definition. It's a manufacturing technique where you take a mold that has a tiny microscopic or even nanoscopic pattern on it. You heat up your material until it's soft and pliable, and then you just press the mold into it. What you get is a perfect, permanent copy of that texture, right on your material's surface. Let's break that down into 4 simple steps. First, you need a master mold. Think of this as the original, perfect copy of the pattern you want. Second, you take your material, the substrate, and you heat it up so it can take an impression. Third, you press that mold right in, transferring the pattern with amazing precision. And finally, step 4, you let it all cool down, the texture becomes permanent, and you pop it off the mold. That's it. It's simple, it's efficient, and you can do it over and over again. But the real magic here isn't just in how it's done, but in what you can do it with. The whole process is unbelievably versatile, which opens the door to a huge variety of materials and different methods. So this recipe really has 3 main ingredients. You've got the mold, your master copy, which can be made from ultra-precise silicon, super durable metals, or even quick and dirty 3D printed resins for fast prototyping. Then you have the substrate, that's your canvas, the material getting the pattern. And finally, you have the process itself, which you can tweak depending on what you need, from classic hot embossing to crazy fast roll-to-roll production that just spits out textured material. And just look at the range of canvases you can play with. You can emboss clear acrylic to make thousands of tiny lenses that focus sunlight. You can use a bio-based plastic like PLA to create those holographic security stickers you see everywhere. You can even emboss something called liquid crystal elastomers to make flexible, smart surfaces that literally react to heat or light. And of course, you can emboss good old-fashioned glass for incredibly high-performance optics. Now, this whole technique comes in 2 main flavors. Hot embossing is that classic waffle iron method we talked about. Heat it, press it, cool it. It's super robust and works great for a lot of plastics. But then there's UV embossing. This is a bit different. You press a mold into a special liquid resin, and then you hit it with a blast of UV light, which hardens it almost instantly. It is incredibly fast and perfect for copying really, really tiny nanostructures. All right, this is where things get really, really cool. We've seen how it works, but what can this technology actually do? This is where these tiny, invisible patterns start to have a huge, very visible impact on our world. So one of the biggest playgrounds for this tech is optics. Anything to do with light. By embossing a surface with just the right pattern, you can suddenly control light with incredible precision. You can bend it, you can focus it, or you can even make light pass through a material that would normally just reflect it away. Get this. Researchers took a piece of infrared glass and embossed a tiny pyramid pattern on both sides. The result? A nearly 80% increase in the amount of light that passed straight through. And that's not a chemical coating, it's just texture. A simple change like that means more efficient solar cells and much better cameras for night vision, all because of a pattern. It can even create color out of thin air, no joke. By embossing nanoscale ridges onto a surface, you can trick it into reflecting only certain wavelengths of light. This is called structural color. It's the exact same physics that gives a butterfly's wings their incredible shimmer. This is being used to make vivid, ink-free colors for anti-counterfeiting labels that are almost impossible to fake. And the applications go way beyond light. This is also tackling another critical area: energy. Microembossing is being used to solve some of the biggest headaches in how we store and use power, especially when it comes to batteries. Okay, so for a battery to charge faster, the lithium ions inside need to be able to move around easily. Researchers are now using embossing to stamp microscopic channels directly into the battery anode, creating a superhighway for those ions. And when you compare it to a high-tech process like zapping it with a laser, embossing is faster, cheaper, and more consistent. The bottom line? Better batteries that are easier to make.
And how's this for some sci-fi tech? Using a special kind of hybrid embossing, scientists can create transparent electrodes that have a silver mesh embedded right inside them. These things are see-through, they conduct electricity really well, and they are incredibly tough. You can bend them and expose them to all sorts of nasty conditions, and their performance barely even drops. Just think about flexible phone screens or transparent heaters for your car's windshield.
Okay, now we are venturing into some truly futuristic stuff. We're not just making surfaces with static properties anymore. With embossing, we can start to build surfaces that are dynamic, that are responsive, that are almost alive. Just look at this quote. Scientists are now embossing those liquid crystal elastomers we talked about to create surfaces that are reprogrammable. What does that mean? It means you can create a pattern, and then you can erase it with a little bit of heat and write a totally new one. These are surfaces that can heal themselves and literally change their function whenever you want them to. And what about making things repel water? Well, a normal piece of polystyrene loves water. It's hydrophilic, meaning a water droplet will spread right out. But by embossing it with a special moth-eye texture, researchers pushed its water contact angle to an incredible 143 degrees. To put that in perspective, anything over 90 is considered water repellent. This thing is super hydrophobic. Water just beads up and rolls right off, just like you see on a lotus leaf. And the list just keeps on going. By using 3D printed molds, researchers can go from a design on a computer to a finished lab-on-a-chip device in less than a week. People are using it to create microtextures that dramatically cut down on friction and wear. It's even being used to make tiny polymer wicks that pull heat away from flexible electronics so they don't overheat. So, after seeing all of this incredible stuff, you have to ask, where is this technology going? What's the next big impression it's going to make on our world? Here's the most important thing to remember. Microembossing isn't just a single solution to a single problem. It's a fundamental tool. It's a platform technology. You can think of it like a printing press, but instead of printing words, it's printing physical functions like water repellency or antireflection or color directly onto the surface of pretty much anything. And we are just getting started. We're now seeing the very first generation of truly dynamic materials built with this technique. There was one research team that created a butterfly-inspired device that can flap its own wings and change color just by shining a light on it. These aren't just static objects anymore. They're becoming tiny, functional machines.
And that brings us to one last, kind of mind-blowing thought. For basically all of human history, a material's properties were just a given. You had to accept them. But now, we're learning how to write new properties, new abilities, directly onto the surfaces all around us. So the question isn't just, what can we make anymore? It's, what do we want our world to be able to do?